that off. Okay, welcome everyone for today's seminar. It's a pleasure to welcome Thomas Herbst, who's at the Institute of Quantum Optics and Quantum Information in Austria. Thomas is currently working in La Palma on an interesting experiment called quantum teleportation from La Palma to Tenerife, which he will talk about today.
Okay. Okay, thank you very much for this introduction. Well, yes, my name is Thomas Herbst, and here's my colleague Xiaosong Ma, Dr. Xiaosong Ma. And we are from the Institute for Quantum Optics and Quantum Information in Vienna. And I want to talk about quantum teleportation, so free space quantum teleportation over long distance. Long distance in our case means 144 kilometers between the Jacobus Captain telescope on La Palma and the optical ground station in Tenerife. And what you can see here, if this is working, yeah, is our green tracking laser. So that's not the signal channel, but it's just for tracking to align the platform of our sending telescope to point to Tenerife. And this is, as I guess you will know, this is the OGS building, and of course Theta in the background. So before I start, I want to clear up some misconceptions about teleportation. So first, I want to mention that physical objects cannot be teleported, at least as the theory is right now and state of the art, let's say. And second is that teleportation cannot be used to do a transfer of information with speed faster than light. So what I will talk about is what we teleport in the end. What do we need for the quantum teleportation and how we realize it in our case. So we teleport a so-called quantum state. This is a wave function of a quantum object. For instance, in the classical physics, you can have a classical bit with either value 0 or 1. And in quantum physics, you can have a superposition of 0 and 1 as well. So you can have 0 plus 1 and the superposition of both values. So you can show this superposition. You can draw it on a so-called Bloch sphere, where 0 would be down here, 1 is here up, and the rest is a superposition of 0 and 1 with different phase between the two. In our case, the 0 and 1 corresponds to horizontal polarization and vertical polarization, because this is really easy to handle. You just need a half-wave plate to rotate from H, for instance, to a superposition state, or you can do any arbitrary rotation with quarter wave, half-wave, and quarter wave plate. And if you, so let's say the translation from the 0 and 1 to the H and V is then called Poincaré sphere. I mean, it's more or less the same as the Bloch sphere, but just instead of 0 and 1, you use H and V. So what do we need for teleportation? Can't we just copy the state and send it away? No, because in quantum theory, there's the so-called non-cloning theorem. So you can imagine this is kind of like a blank sheet of paper, and you want to copy the contents here onto this blank sheet of paper. So what you get here is, if you copy it, it's 0, 0, because the first one is 0. And here, if this is 1, then the 1 will be copied over here, so you will end up with 1, 1. So if you want to do copy a superposition, it will end up like this, that you will copy the 0 and the 1. So you will end up with 0, 0 and 1, 1. But what we actually would need is to copy the whole superposition onto this blank sheet of paper. And this would it should look like this. And then if you factorize it, it looks like this. And you can clearly see that this is not the same as above. So it's not possible to clone a superposition. And the more artistic explanation or artistic view of this is, if you have a vertical polarized photon, you try to copy it You copy it, it both go through the beam splitter. If you have a horizontal, you copy it, both are reflected. But if you use a superposition, so 45 degrees, for instance, they don't go, they are split, that's it. You can't copy this superposition. And yeah, the linearity of quantum mechanics prohibits this cloning of arbitrary states. How to circumvent this non-cloning theorem? It was proposed by Bennett et al. To do in 1993 to do a classical teleportation. You have an input state, you measure it, you get knowledge about the state, and then you have a source and prepare the exact same copy of the state, and you have an output state. In this classical teleportation scheme, you can get 66%, so 2/3 average state fidelity. So what happens when you use a quantum resource? So for instance, in 1935, Einstein, Podolsky, Rosen, they proposed in their famous paper the so-called EPR source. It is a source for entangled photons. And I give you this. It's a source for entangled photons or entangled particles, let's say. So you have a source, it emits two particles, and these two particles are in a special relation, so they are correlated with each other. And these correlations can be can be written in the so-called maximum entangled Bell states. And these maximum entangled Bell states are this called psi minus state. It's an antisymmetric state. Psi plus state, phi minus, and phi plus. So the correlations of the overall system, so of both particles together, are fixed or well defined. But if you measure only one of the two particles, you cannot you will get random results. So it's not fixed, let's say. And this is what this correlation will hold if you separate the particles arbitrarily far away. This correlation still will hold, and this is what Einstein called an spooky action at a distance, what he couldn't imagine that this can be true, let's say. And then in 1964, Bell formulated his so-called Bell inequality to show which holds for local realistic theories. And if you're able to violate this so-called Bell inequality, you know that you have a quantum state. So what we are trying in our experiments, or what we tried before, is to violate this Bell inequality, and this we did in 2007, and this to show that it is a quantum state, the two particles. And Clauser, Horn, Shimoni, Holt, they in 1969, they reformulated this Bell inequality to inequality for experimental, to use in experiments, let's say. So Bennett et al., they proposed in 1993 a so-called quantum teleportation scheme, and this combines the classical channel and the quantum channel. So how this quantum teleportation works is you need this so-called EPR source, so this source for entangled photons. In our case, we use the entangled photons in the psi minus state. And you need an input state, which is a superposition of 0 and 1, any arbitrary superposition of 0 and 1. And you project this input state with one of the two photons of the two entangled photons. You project them again in a Bell state here with the so-called Bell state measurement. And due to the output, depending on the output of this Bell state measurement, you have to send information to Bob. Yeah, first I want to say Alice and Bob are normally the names in our community for the two parties. So Alice on one side and Bob on the other side. Normally Alice is the sender and Bob the receiver, more or less. And then Bob has to do the unitary transformation on his entangled particle, and depending on the outcome of this Bell state measurement, and then you will end up with exactly the same state here as you put in here. So if you look at this formula, for the total state, you have the input state and matrix multiplication with the entangled state. you can then rearrange and reformulate this equation in the basis of the Bell states between particle 1 and 2, so between the input and particle 2 of the entangled. And then you can see, for instance, if you measure at the Bell state measurement here, if you measure a psi minus state between particle 1 and 2, particle 3 is alpha 0 plus beta 1, and this is exactly the same as here. So in this case, the unitary transformation is the identity. Okay. And you can see that we also need this classical channel to transfer the information, the outcome of this Bell state measurement here to Bob. So this limits our speed of the information, let's say. So that's why you cannot use quantum teleportation for faster than speed of light communication. So what we need for our quantum teleportation is the single photon input here, the quantum channel with the EPR source, the Bell state measurement here, and the feed-forward channel, the classical information, the outcome of the Bell state measurement, and then we have to do a fast unitary transformation. So how we realize this? So the quantum channel, for creating these entangled photons, we use so-called polarization entangled photon pairs with a type 2 spontaneous parametric down conversion in a so-called beta barium borate crystal. And so you pump this special nonlinear crystal, you pump it with, in our case, 405 nanometer light, and then you, this input light, out of this are created two photons in these cones. They are output in these two cones, anywhere in these two cones, and for the two photons, momentum and energy conservation has to hold. And what we do is, at these intersection lines between the two cones, we look at the photons, so here are the points, and for instance, in the upper cone, all photons are horizontally polarized, in the lower cone, all photons are vertically polarized. So if you look at this intersection and you get one photon, you don't know if it's from the lower or from the upper cone. So you get, for instance, here V, then you know here you must have H polarization, because here you took, let's say, the photon from the upper cone, and then here you took it from the lower cone. And this is how you get this entanglement. So you will not know before you measure, you will not know if you get here H or V, but if you measure this, if you know what you got here, you know that in the other intersection point you will get the opposite polarization. So, and these polarization entangled photons can be written in the so-called, in these Bell states, Bell states. So these symmetric Bell states, the phi plus, phi minus, psi plus, and this psi minus is an antisymmetric Bell state. So this means when you interchange the particle numbers, you will still end up with the same state, but so these are bosonic states, let's say, and is a fermionic state. And if you interchange the particle numbers here, then you will end up with the same state, but with a minus sign in front. So the next prerequisite for our teleportation experiment is the so-called Bell state measurement. And what we can do with our Bell state measurement is we can distinguish 2 out of these 4 Bell states from the slide before. So this Bell state we can tell, and this Bell state we can tell. These 2 we cannot tell, because therefore we would need number resolvent detectors, which is not available right now. So to distinguish these 2 of the 4 Bell states, we use a photon interferometry at the beam splitter. You need indistinguishable inputs, and Hongo Mandel they did this interferometry in 1987, and they showed the so-called Hongo Mandel dip. So we use this EPR source, so the source of entangled photons. One photon impinges from one side, the other from the other side on the beam splitter. And then you have for the psi minus state, so for the fermionic input, you have the following possibility: either both photons transmit the beam splitter, or both photons are reflected. But they will always take opposite exits, because this state here is an antisymmetric state. So they don't want to take the same exit. So this means when you do a measurement of with changing the delay between the two photons arriving at the beam splitter, and you are exactly at the 0 delay, you will see that the probability that you get a coincidence between this and this detector goes to 1, or to a maximum. Because when they are indistinguishable at the beam splitter, they will always use opposite exits of the beam splitter. If you use the psi minus for the psi minus states, it's a symmetric state, it's the opposite. So the probability goes to 0 that you get the coincidence between these two detectors. And here you can again do this measurement with delay between the two photons, and you see that the probability of getting a coincidence drops to 0. So the teleportation of a photonic polarization state looks now like this. As I told you already, you have the input state, you do a Bell state measurement with one of the entangled photons. You forward the information, the outcome of this Bell state measurement to Bob, and Bob does a unitary transformation depending on the outcome of this Bell state measurement. And then you will end up with the output state exactly the same as the input state. So you reformulate you rewrite this formula in the basis of Bell states between particle 1 and 2. And for instance, if you measure a Bell state with this Bell state measurement, if you measure the psi minus Bell state between particle 1 and 2, you see that the output over here, the output state is exactly the same as the input state here. So you input alpha H plus beta V, and you get alpha H plus beta V. If you measure a psi plus at this Bell state measurement, you will end up with alpha H minus beta V, and therefore you have to introduce a unitary transformation to get the same input state as here. So to get the output state the same as the input state. And this is done by a half-wave plate. So you rotate, or you introduce a phase. So the first realization of this quantum teleportation was done by Dirk Baumeister et al., and it was published in Nature. And this quantum teleportation had quite an impact in the science community. For instance, Nature, they collected the most important articles since 1869, and in this collection, amongst the finding of DNA and the explanation of neutrinos, it's also the quantum teleportation mentioned. And they also have a collection of milestones of Nature articles and regarding photons, and it's all the experimental quantum teleportation is also mentioned here. So it had quite an impact. And a colleague of us, he did as well a quantum teleportation experiment because people tried to separate the two particles further and further, or the two parties. And the first experiments were in the lab, like over a distance over, let's say, 20 centimeters or something. And our colleague Rupert Ursin et al., he published in 2004 a teleportation across the Danube in Vienna. And he used, as a quantum channel, he used a glass fiber cable under the Danube and the feed-forward link, so to forward the classical information of the Bell state measurement at Alice, to forward it to Bob, he used RF signal. So what we are trying to do now is to further separate the parties. And so we have our sender, or Alice, we have on La Palma at the Jacobus Kapteyn telescope. There we produce these entangled photons. One of the photons is one of the photons, there's done a Bell state measurement together with the input photon. So this is the input photon source. Here's done the Bell state measurement. And depending on the outcome of this Bell state measurement, you do coincidence measurements between these detector clicks. You feed forward with the 1064 nanometer laser. You forward with blinking, let's say. So 1 blink for psi minus and 2 blinks for psi plus. You forward this information to Bob at the OGS in Tenerife. And depending on this outcome, a unitary transformation with a electro-optical with a pocket cell is done. To track the two telescopes at each other, we use green beacon lasers. So we shine with a green laser to the OGS and from the OGS to La Palma. And then we collect, for instance, in La Palma, we collect the light with a lens and try to keep the spot on a CCD stable, so the whole platform moves such that the spot always is at the same position of the CCD. And the same is done at the OGS, so the green light will be fed through to a tracking CCD, and the whole 1 meter telescope tracks like every second to keep the star at the horizon at the same position at the CCD, let's say. In this scheme, we just sent the entangled photon, so the photon 3, which is the one to be for teleportation. We send over the quantum channel to the OGS, and it's also collected, and then here it's rotated. And the problem in our case is that due to the long distance, and you have a lot of loss, and we try to decrease this loss and increase the link efficiency between the two islands. And therefore, we are also trying, or we want to try in the future, to use an adaptive optic system to pre-compensate for turbulences in the atmosphere. And this would work like this, that you use a 785 nanometer beacon laser, shining over from Tenerife to La Palma, collect the light through the system where you also want to send out in the end. With a tip tilt mirror, a deformable mirror, then you split the input signal from the quantum channel and look at the power you get at the detector, and then you perform a so-called parallel gradient descent algorithm. And with this algorithm, you try to stochastically change the actuators of these mirrors such that you increase the power at this detector here. And then when you have maximum power, let's say, the mirrors compensate for the atmospheric effects over the link, and the photon going out, so the entangled photon going out, will go through these mirrors and be pre-distorted such that the atmosphere kind of corrects again the wavefront, and we hope to get a better link efficiency like this and a smaller beam size over here. Because one has to imagine that if we send over here with a 7 centimeter lens, as we do right now, we will end up with around 8 meter diameter beam at Tenerife, and we have a 1 meter telescope, so we cut out only a small portion of the whole signal channel, and this gives us, in good cases, 30 dB loss. So only one of 1,000 photons we detect. The experimental setup in detail, and this is in the JKT on La Palma. So we have a 80 megahertz pulsed laser with 150 femtoseconds pulses. It produces 808 nanometer light. It's up-converted in this so-called BBO crystal to 404 nanometers. Then, again with the BBO crystal, it is down-converted, and this up-conversion is quite efficient, but the down-conversion is very inefficient because it's a spontaneous process, and this spontaneous process is very unlikely, so we get only very few of entangled photons out of this pump beam. And this pump beam is quite strong, so several watts. So here we get, for instance, one photon which is to be sent to Tenerife in the end, and this other photon here from the entangled photons is fed to the Bell state measurement, and here we produce again out of the pump beam two photons, and at the beam splitter one of them is split away, and if this detector clicks, then it is a trigger that there is a second photon in the system, and we know that there should be a Bell state measurement. So what we did in the lab in Vienna is we tested our setup with a 30 dB filter because we expect a 30 dB loss. And we could show that for all bases, we could show that we in our state fidelity is above the classical bound of the 66%. And so we had an average of 80.8% state fidelity with this 30 dB attenuation. Now to give you a short glimpse at the setup, let's say, this is how the setup looks right now in the JKT. So this is the strong laser, and then you go through here, and yeah, you have a lot of optic stuff in between, and you probably know this as well, such stuff. A lot of Toilets components. Okay, so, and I want to thank, of course, the ING group and the IAC group. So Angel Alonso, I saw he is here. Thank you very much for helping us last week. And yeah, that's so far from my side. Thank you very much.
Are there any questions or comments?
I have a question related to the distance between the observatories. So why do you have decided to make a long baseline? Is it because you constrain much better this Bell's inequality, or so what is the reason of doing this between the
So more or less to show that the quantum state or that this teleportation also works over this long distance. And I mean it's quite difficult to find a place where you have a telescope on one island and a telescope on the another island. I think there would be Hawaii as well, but Hawaii is not that far separated, the island. And in the end, we chose the Canary Islands.
Is the distance playing any important role in terms of constraining the theory, or not?
Well, I mean, there are always people claiming like maybe the quantum state doesn't hold longer than, let's say, 1 kilometer. And if you can show the further you separate the parties and it still holds, you can show these people that in principle it should be arbitrary over arbitrary distance. Mm-hmm. 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 So, for instance, this quantum teleportation can be used for repeating signals, which is not possible right now. So, for instance, if you use a glass fiber, after 100 kilometers, you end up with almost nothing because of all the loss in the fiber. And also, if you go through free space, you get losses and everything. And at some point, you have to amplify and resend the signal that you sent at the beginning again. And for this, you could use the quantum teleportation in the end. Yes. Yes. Okay, so, well, the problem is that, I mean, with this quantum information, you can, in future, you could encode more dense than with classical information, because you can also use this superposition in contrast to classical signals.
Further questions, comments? If not, can we thank our speaker one more time?
Thank you very much.